All right, so almost 5 years ago, when I started building my first neural net model, nobody told me that I have to have these bunch of considerations before I could select my own ML algorithms. After working for so many products in Google, for Play Stores, for Chrome content recommendation, finally I have realized that it is not just the ML algorithm. There are three important lessons I have learned, which I would like to share with you guys today. And before I jump into it, I would like to request, if there are any questions in the middle of the presentation, feel free to stop me and ask. The first lesson I learned is logging. Now you guys may think, why I'm talking about logging, right? Logging is there since the dawn of software. However, with ML models, I think all of you know, logging has played a really critical role. It generates training data for us. So in typical software, you will see something like this, right? You will have your app that will generate logs, you will get some training data out of it, you will create model, and then you will deploy it, and you go your way. Not so fast. There is an important step there at serving time, because when you deploy your model, you need to pull up all your features which you used for your model, and this is a very critical step. Many times we build our awesome models, and when we go in production, we don't have way to pull these features at a serving time. And I learned this lesson hard way. When I started building content recommendation system for Chrome, we built something like this. Idea is very simple. The user is on this page. In this case, it's a Audi car, and we are giving all the suggestions from the drop down. So Mercedes, BMW, something like that. And first, when we built the model, we realized that just the URL is not good enough to build any model, right? Because it's just a long string. We did tokenization, we did a lot of techniques, but just the URL was not good enough. So we thought, let me bring something more to it. So we started pulling knowledge graph entities about this page. Now, what is knowledge graph entities? Knowledge graph entities are just the places, people, and facts about the web page. So when we pulled these knowledge graph entities about the page and started predicting the next URL the user is interested in, then model improved a lot. So we said, yeah, really good. So we went to our production team and we said, okay, this model is great, we are ready to deploy. And they said, sure. However, as soon as we deployed it, we realized that we are not logging these knowledge graph entities with our logs. That means there is no way to pull these knowledge graph entities at serving time. So we scrambled at the production time. We said, okay, now what can we do? So we thought, okay, let's make a RPC call to this external server and grab all these knowledge graph entities for our model. We did that. However, the latency comes into play. Our latency budget was 10 millisecond, and with this just 10 millisecond budget, there was no way we could go out and pull these knowledge graph entities and serve our model. What next? So we built a huge cache, and that in the cache, we just dumped all the popular entities and popular web pages. So we will take the latency hit for the first time, but after that, it is like available in the cache. So we can pull it up and then serve our model. So lesson learned, whenever we have a logging infrastructure, we have to make sure there is a lookup functionality out of it, so that when we serve our models, we can pull these features when we are building these models. Now, that's the first lesson. Second is training versus serving skew. Like I gave a hint in my last example, whenever you have features, you need to make sure those features are available at the serving time. And whenever these features are not available, these training versus serving skew comes into play. And this is a common source of bug I have seen in multiple systems. It's not just one system. Whenever we go, we make sure that if the system is there, are we able to grab all the metadata, all the features we use at training time at serving as well. And it is not just a technical problem, it's a organizational problem, because when you have some model, especially large scale ML models, complicated models, there will be a heuristic team which will build the model based on some heuristics, because until you have the training data, you cannot build any models. So you will have something like this, that you will have a client request which is going to server, and then server will have some logs. Once this bottom approach is there, then somebody in the leadership team thinks, oh, why not we improve our system with some machine learning, and they bring bunch of data scientists, and data scientists have that training data generation and then ML model built up over there, right? So the training data generation and ML model comes later in the life cycle of a software, and that means that any data they are pulling, like a metadata from other systems, that will not be available at the serving time. Now, what's the solution for this? The best solution I have found is just move that metadata at the serving time. If you have that metadata information at serving time, you will have your model with all the features. However, what I have seen in my past experience, moving that metadata pull up in serving time is not as easy as just writing some bunch of software. And the reason is, when you are going to change any production system, you will have to justify that why you are adding this extra complexity, why you are adding this extra latency. So the production team, which was there before the ML team was formed, they will say that, give me some proof that your ML model is worth anything. So you will say that, let me run some live experiment and I will prove it to you. And to run those live experiments, you need that metadata at serving time. So it's a chicken and egg problem. So what we have done in our projects, what we do, we just add the code under some flags, and then we run those live experiments only by enabling that flag. So that flag will not be available for, say, 99% of the users, and it will be running for 1% of the users. So that's one way we figured out that once the live experiment is positive, then we can run, have this metadata information in the serving, and we go our way. The third lesson is latency. Now, latency dictates what architecture to use, because if you have a very short budget like we had in our content recommendation system, we cannot have very big architectural model which is running into seconds sometimes. And in my past experience, I have seen three types of model from the latency perspective. These are offline, cache-based, and online. In offline model, we have a model where we can have as complicated model as we want. We can run it in a batch mode and then store all these information in a lookup table. And lookup tables are really fast, right? So you don't have to worry about the latency. However, this lookup table based approach becomes very stale sometimes, because you are running in a batch mode. You may run it twice a day or thrice a day, but during that time the model is just not working, right? Whatever you calculated in the morning, that serving will be there for the whole till the next time, right? But in case of a news, this may work, right? Because headlines doesn't change so often. So you can run your model and you can store this in a lookup table and then serve your model. The second is cache based, is like the middle ground between offline and online, which we built for our Chrome content recommendation, where you are doing the model inference, but we are storing it in the cache, and then with the TTL, which is tweaked based on the production, we can store it for, say, 3 hours or 3 days. It is in our control. So that's the middle ground sometimes we have to figure out. And the last one is, of course, online, where we have to run the model every time. And there are cases, say, keyboard suggestions. So in keyboard suggestions, the user input is changing every time. So we cannot store the predictions in some lookup table. And on top of that, sometimes we have to run it in a very tight constraint. The latency there in online models for, say, keyboard suggestion is very tight. So we have to squeeze the model in such a small size and put it on device itself. So all our keyboard prediction model is on device, because we cannot take the hit of even a round trip to the server. So in conclusion, what I have learned from my all building all these ML system, that these three important pillars rarely get the attention they deserve. So next time when you are going to solve your problem and picking up your favorite ML infrastructure, please give some consideration to these 3 points, and I assure you, your life it will be much more smoother when you put your system to scale to real-time users. Thank you.
We have time for questions, if you have any. Sorry, Chris.
I was just curious, what all apps or devices have you worked on for these kinds of projects? Like, is that Android, Chrome, or?
Yes. So to give you one example about App Store, about Play Store app recommendation. So there we built a personalized app recommendation model for Play Store, and when we built those models, it was on server side. So we thought let's add a country, user's country, to the app recommendation model to personalize it. Suppose you are in US and the apps are popular in US. So we thought, okay, let's add the country, and offline model was really good, and we ran our offline metrics, and then we went to live experiment. We made sure that the country is there at the serving time also, so that there is no training versus serving skew. However, our results were very neutral. It was not very encouraging, and we realized that after debugging it for weeks, our models and everything was perfect. However, there were many Android devices which were very old and running very old Play Store, and there the country was not being filled. So it was being filled at like say 10% of the time, and 90% of the time it was not filled. So when we verified that country is available, that it is there for some time, and sometimes it was not there. So there we again got bitten by training versus serving skew. So that's one example. Another I gave about the Chrome, and then the third one is keyboard suggestions. Any other questions?
Thank you very much, Manoj.